Okay, let's talk irreducibility in the context of this renewal chain. So the question that's being asked of us is, what are the conditions under which this renewal chain is irreducible? So the first thing we want to dig into are the words conditions. What does that mean? And let's also revisit what irreducibility means. So let's take the easy one first. So irreducibility, hopefully you recall, it means that for any pair of states, let's say x and y, there's going to be a finite number k such that the k-step transition probability of going from x to y is strictly greater than 0. So one important thing is that you do not need this k to be the same for all states. So if I'm looking, for example, for a valid number k with which I can go from state 2 to 3 in a finite amount of time, that k doesn't need to be the same as if the same question is being asked about states 1 and 4. Right? So easy to see that from, let's say I want to move from state 2 to state 3. So clearly there's no way to do it in one step. I cannot move backwards, but I can clearly always get to 0. And then I can take one more step, my third step, if provided that Q3 was greater than 0, then there's going to be a positive probability of doing it in 3 steps, going from 2 to 3 via 1, 0, and then 3 in 3 steps. That does not mean that 3 needs to be that number that holds for all pairs. Certainly not. It's not going to hold for, some state, let's say 4 and state 60. Right? That's not going to happen, because even when you start from 4, you're going to waste at least 4 steps to get to 0, which is the only state on your way to getting to state 60. So hopefully that's all clear. The only other remark regarding irreducibility is that when not mentioned, the definition of irreducibility always pertains to the state space, right? So this is not irreducibility for some subset of states, which is a possible question. Here it's not mentioning any specific subset, and so you assume that this is going to be the case with the state space, which here is identified with the natural numbers. So you want to make sure that for every pair ij, there exists a k, which may be specific to the ij, such that this k-step transition probability is greater than 0. So, just thinking about this out loud, what are the conditions of irreducibility? And here, I guess we do want to spell out what conditions mean. Conditions here means what are the parameters that define the renewal chain? What are they allowed to be, right? And the only parameters here are these qx. We're constrained to making the qx non-negative and sum to 1, but besides that, I can do pretty much whatever I want. And so the question is basically trying to force us to come up with a clean condition on the q's such that the chain is irreducible. So based on kind of some of these examples of getting, say, from 2 to 3 that we've discussed, one observation is that if I'm looking for irreducibility between I and j, and I is less than j, there is no way to, actually let's do it the other way. If we're looking for irreducibility and checking states I and j when I is greater than j, right? That means on this diagram, I is going to be to the right of j, so j is going to be somewhere here, I is going to be here. The probability is always going to be 1, because in amount time given by I minus j, where did I put the I? I said I was here and j was here, right? So in the amount of time I minus j, you move from I to j, and that has probability 1, which is clearly greater than 0. So it seems reasonable to say that the only difficulty is going to be when I is less than j, so I is on this side and j is somewhere to the right. And here we can almost reduce the problem to the, we can kind of observe the fact that from I'm always going to move to state 0. Right, and j is now going to be on the way because j is greater than I. So the first thing that we're going to observe that's going to happen is that from state I, we're going to go to state 0, and then finally at this point we have a chance to reach state j. And so now we just need to make sure that there is always some positive chance of reaching state j. And so one possible kind of condition you could come up with is that there are infinitely many x for which qx is greater than 0. This is not the best such condition, but let's just kind of think through whether this would guarantee that I move from I to j with I less than j, in a finite many steps with a positive probability. Well, this seems reasonable. So what this is telling me is that there's going to be some qx with x greater than j, right, beyond j. So again, the setup was we started at state I, we always know that we moved to 0, now we must get to j, and this condition is guaranteeing me by claiming that there are infinitely many, and infinitely doesn't mean for every single integer x in the state space. That's not what this is saying. It's just saying there are infinitely many, there are infinite subsets of the natural numbers. But I can always find a qx which is greater than 0. So all I'm being, all this condition, the way this condition is helping me is saying, well, look, there's going to be a state x greater than j, using which there's a positive probability of transitioning all the way past j. Right? I don't need to transition to j directly from 0. The key observation is that you can transition past j, because once you do that, you can always come back to j deterministically, and you're always guaranteed that trip. So, this seems like a reasonable condition, but it's a little bit, it's a little wordy. Let's also, maybe before we kind of try to clean it up, let's try to think about what negating that condition would mean. If we claim that this condition guarantees us irreducibility, then the negation of this statement should guarantee that irreducibility is violated. So what's the negation of this? There must be infinitely many x for which qx is greater than 0. The negative must be that there are only finitely many qx for which qx is greater than 0. So what would that mean? If there are only finitely many, I can find the largest number n, right? The very last n for which qn is strictly positive. And I know that everything past that, qn plus 1, qn plus 2, qn plus 3, all of them are all 0. And now I have immediately an example of no way to get from, say, state 0 to any qn plus something, right? And so this seems to hold, right? That this seems like we've really checked, we've come up with, essentially a proof, right? That says that under this condition, I've demonstrated exactly how, with positive probability, I get from any state to any other, from any I to j. And the negation of that also seems to work in that we immediately have an example of where specifically that irreducibility is being violated. And the only thing I want to mention now is that there is maybe a better way to write this condition, and that's through defining this new variable that we're going to use in the context of recurrence. I want to define this qx, capital Qx, and I'm going to write it as the sum of all y greater than x, and I'm going to sum up the qy's. Okay, so this is kind of a cumulative probability. This is, in fact, you could look at this, you could think about this as the cumulative distribution function of the probability q. But what is, just very quickly, how do we describe what's the meaning for qx? Well, it's the probability that we transition from 0 past state x, right? That's what it's saying, that we're going to go either to state x, or to state x plus 1, or to state x plus 2. And that's exactly what came up in this discussion of how we get from I to j. We needed to go past j from 0. And that's what this is quantifying, right? This is exactly telling me that if qx is greater than 0, then I know there is a positive chance, a positive probability of going beyond x, going to some state after larger than x. And so a much better way, or maybe a cleaner way, to state a condition for irreducibility is obviously then to just say that a chain is irreducible, the renewal chain is irreducible, if and only if this qx, right, big qx, is strictly greater than 0 for every x. Because that's telling me that for every state x, I can move from 0 beyond it, right? And if once I move beyond it, I can come back to it, right, in this deterministic way, because every single probability backwards is a unit probability. So hopefully that helps. I won't write the final condition on the board, but it's basically qx is, right, has to be greater than 0 for all x, right? That's going to be my final answer.